I'm Mathew George, and this is Wen Zin, both of us from Microsoft. He has been taking over a lot of the core SMB and the chore too. So development for the last couple of years now. So 1 year?
1 year.
1 year, okay. So he has been experimenting quite a bit with a lot of the transport layer stuff and the lower layers of the SMB stack. And he'll be doing some of the performance work and some of the stuff which he has done second half of the talk. So I'm going to give you a high-level summary of what's been going on and where things are moving and that kind of stuff.
So is this an upgrade?
Yeah. All right. So where is SMB3 today? As I know, over the last 10 years or so, I think me and David Cruzy, for a lot of people who have been here for the last several years, we have been working on SMB3, trying to improve it, get it performing well in the data center, and so on. So where do we see the maximum uptake of SMB3 today? So the first and the most important one is a software-defined data center or private cloud or whatever way you want to define it. And we have seen a lot of the features that we have done in the last several years, multichannel and RDMA and better encryption signing. Pretty much everything ties into data center workloads. And we have seen a lot of adoption of SMB there, primarily in the Scaleout file server for applications. So to run your applications like databases, hypervisor, VMs, that kind of stuff. And then more recently, inside Microsoft, we have been using SMB as a transport for several other application workloads. And one of them is Storage Spaces Direct, which basically is a system designed to cluster together disks on individual machines in a cluster and then export them over the network so that other machines in the cluster can see these disks in a shared pool. And S2D, or Storage Spaces Direct, uses SMB3 as transport, and they rely on RDMA and multichannel and a lot of the may not be so much of the failover capabilities, but the network resilience portion of SMB3, as well as the high performance we offer and the security we offer, they use it extensively. And the second scenario which we have seen is to use SMB3 as a file access protocol from guest to host, especially in the container scenarios where you have hypervisor VM containers running on a Windows server and you want to access files stored on the host machine. And they use SMB as a transport to access those files. And it's not a regular TCP-based transport. They use the VM bus transport, as they call it. It's the transport which VMs use to communicate to each other, and they run SMB over VM bus. And in fact, we have even done what we call pseudo RDMA over this VM bus transport, which RDMA is just a way of registering memory across so that it's accessible across the network. But so you could do the same thing in a virtual way over VM to host too. And then the other interesting scenario is Azure Files or cloud scale storage, where we are seeing SMB3 being used to access files over the internet. And aligning on these three directions, we have been prototyping a bunch of things. So none of these are actually official or published, and these days the Windows schedules make it kind of unpredictable to plan these things. So we take it as we go and we prototype it, and then things look good, we push it into a release. That's the kind of new release model. The first thing I want to kind of talk about is SMB over QUIC. And for those who are new to QUIC, QUIC is basically invented by Google as a transport protocol for web applications. And we think we can use the QUIC transport as a way of transporting SMB over the internet because it gives you a couple of nice properties. And then Wen is pretty much going to talk about some of the changes to the transform logic in SMB to incorporate new signing algorithms, and we have prototyped compression and so on. And Ben is going to talk about it. Yes, question?
This QUIC thing, I mean, one of the main features is multiple channels inside one connection. How are you going to use that?
Question is, QUIC has support for multiple channels. How are you going to use them? I'll talk about it in a while.
Okay.
All right, and these are few minor updates to the protocol from the last 1 year. So the first is there's a new normalized name query which was added to the protocol document. I don't know if folks have noticed it, but this allows a client to query the full path name for a file in a normalized fashion, so that it basically, if you have like short names in the path, it'll expand them to long names and so on. So, and this is something which is used by all these filters running on Windows, like antivirus folks and stuff, to match path names. So you get a unique path name for a file, essentially. And if we do not support this, the thing gets really chatty, and the system actually opens each folder, does a dir, and then builds up the path name, and it can get quite chatty. So that's why we went ahead and did this. And the second one is improvements to directory caching. This is not a wire visible behavior. This is something that I did on the SMB client, because the directory cache used to be able to support only small directories up to 64 kilobytes in size. So it's not more than a few, maybe 100 entries or so. Now we can support larger directories, and we can enumerate directories in larger chunks to like one meg buffer. So things work much better with the directory cache now. And then the last thing, again, is not protocol visible. When we run workloads like storage spaces direct, which is using SMB as a transport protocol for block storage, a lot of the file system complexity is kind of removed from the picture, because it's just reading and writing blocks. So we have put in some I/O path improvements in the SMB client to shortcut some of these things. Like there are a whole bunch of complexities in the client systems, like locks, synchronization, all that kind of stuff. So you don't need a lot of the stuff for if you're just doing raw disk I/O over SMB. So there were some good gains to be had there to reduce the path length and improve the latency of I/Os. So what is QUIC for? So QUIC is basically a replacement, or I wouldn't call it a replacement for TCP/IP, but it's a replacement for SSL TLS, and Google has been working on it since I think 2012 or 2014, and they have it in their Chrome browser implemented as a library. And it was designed for transporting HTTP traffic, and a lot of the improvements here are kind of tied to HTTP sessions, which are kind of short-lived and things like that. So they have low latency connection setup without, you can do like zero RTT connection setup too, where TCP involves like you have to send a SYN, then a response, and then the data transfer starts. So with QUIC, you can actually transfer data right away without waiting for an act from the peer. So zero RTT connection setup, and then it's encrypted by default. It uses the latest TLS 1.3, I believe, and later algorithms for encryption. And it's all certificate-based and stuff. And then there are a few things which it does above and beyond TCP, and one is multiple streams. So you can set up a QUIC connection and then open up multiple streams underneath it. And this allows you to do two things. One is to avoid these long queue depths and head of line blocking, as you call it. When you queue up a large amount of data, TCP is an in-order transport, so things get stuck behind one another, and packet loss of one packet loss somewhere in the middle means that everything gets backlogged. So multiple streams actually allow you to recover from losses better, recover from congestion better. And the second thing is what they call application layer protocol negotiation. So you could use the same QUIC connection with the same 4 tuples. So you have the local and remote IP addresses and the port numbers. And then on top of that, you could multiplex the same connection for multiple applications. So you could run HTTPS traffic or SMB traffic all on the same underlying 4 tuple. So you don't have to dedicate a port number, which sometimes can help, especially with SMB. And even on the server side, at least on the Windows implementation, you could have both HTTP and SMB, for example, listen on QUIC 443, the SSL port, and then it could get traffic demultiplexed by the stack. And then there are a few other things like connection migration. If you have a wireless and a wired link, it can automatically switch between the two interfaces, cellular, wireless. And then error recovery, I believe they have forward error correction. So intermittent packet losses, you don't need to retransmit. They can reconstruct the packet on the fly. And then the last thing is it's UDP-based library implementation. So you don't need big kernel changes or anything of that sort. You can have UDP sockets. This will work. It's just a library built on top of it. And it's with IETF now in draft stage, but still experimental. And the good part about this is that Google's experiments over the last few years, they've shown that it's quite NAT friendly. You would not expect UDP-based protocols to be NAT friendly, but they found that it works well in about 93% of the cases. So home NAS boxes or NAT routers allow it through. You can punch holes through NAT routers without any external configuration. So it works well. And right now it's software only. So a lot of the work which is done by TCP these days in hardware on the NICs, offloaded to the NICs, it's all done in software. So it is expensive. And I even heard about talks about RDMA, people trying to implement RDMA over QUIC. I don't think there's anything concrete there, but maybe. And there are interoperability concerns. I know that the TLS, some of the authentication and encryption stuff is still not there yet. At least I know the Windows implementation right now is not interoperable with the Google one, but eventually we hope it'll get there. And how do we bind? So this is just talking about our prototype. How do we bind QUIC to SMB? How do we run SMB over QUIC? So I talked about the ALPN, the application layer protocol negotiation. So it's basically a string which identifies your application, and we just shows an application layer identifier for SMB. I believe it's called SMBQ or something of that sort. So. And then, so you can share the same port with HTTPS traffic. And right now, SMB has implementation of multi-channel outside of QUIC. So we can do multiple TCP connections anyways. So I don't immediately see the value of using multiple QUIC channels under the same connection, because we can, at least at this point, we can do better because we can span interfaces and we can use different types of transports and stuff. So right now, QUIC is just used, in our prototype, is just used as a TCP stack replacement with a single channel. There's nothing else other than the fact that you get encryption. And the biggest scenario, I think, which might come out of this work is that we are seeing SMB deployment in the cloud. And TCP 445 has become or at least it's been shown to be a big pain with Comcast, like all the internet providers, ISPs. A lot of them block it. So if we can get SMB traffic to look like SSL traffic, that works well. So that's something which I think is a good motivation for why we are doing this. If we can get this working over the internet, secure, TLS secured stream, running SMB, that will work well. Now, that's what we have for QUIC. We have a prototype running. Perf numbers didn't look good in the initial cut, so I'm not even going to bother talking about it. It's just an initial implementation, but we have it working between a Windows server and a Windows client. And hopefully once the Microsoft QUIC library is interoperable with the Google open source libraries, then we can actually set up something and then see how it works across implementations. The second thing, which more of the detail is going to be given by Wen, but we talked in 2015 SDC about performance of GMAC versus, or AES GCM versus AES CCM. CCM is the current signing algorithm in SMB 3.1. And we know that GCM performs significantly better in terms of CPU usage. And we want to change the signing algorithm in SMB3 to use GMAC, or the HMAC version of GCM, AES GCM. And most CPUs have optimized instructions for GCM. Now, the other design question is, well, SMB signing, when it was done, it is actually embedded into the SMB portion of the protocol. It's actually in the SMB2 header, right? But when we went ahead and did encryption, it was done as a layer above SMB2. You have the transform header. So this has been something which we have been debating internally, whether we want to just use the transform header going forward for signing and encryption, because if we make new algorithms, if you want to add features and stuff, it might be easier from a layering perspective to keep it at a separate layer rather than in the SMB2 header. But there's no evidence either way. There are reasons why you could do it. So one is better layering, and then the signing and encryption, they all use the same algorithms. One, they use AES GCM to sign versus encrypt. It's pretty much the same kind of operations which happen underneath the cover. So unification helps. But there is an extra cost of usually buffering the data, because if you do it at a separate layer, the transform layer will have to receive the entire data, then it verifies the signature and then hands it up over to the upper layer. While with the SMB2 built-in signing, we do signing, at least on the client, we do signing computations piecemeal. So as and when we receive the data, we compute the signature, copy it into the user's buffer, and so on. So it's a little bit, there's a extra copy which might be involved in the transform path. So we haven't fully evaluated which way we'll go, but that's something that we are considering to unify encryption and signing going forward. The other big thing is RDMA and signing. So when initially people brought this up, we think, why would anybody spend like thousands of dollars on their RDMA hardware and then turn on signing just to ruin their performance? And turns out that a lot of people just do this. And often it's beyond, it's their corporate mandated policies, right? People pull down security policies from their domain controllers or whatever, and they go and force signing everywhere, including their data centers where they have RDMA networks. So whether it's a good thing or not, people end up doing it. And when you turn on signing on RDMA, things which happen are not often understood well by the customer. So what happens when you turn on signing on RDMA? What people observe is that if you have just 10 gig Ethernet versus 10 gig RDMA, Ethernet TCP over 10 gig Ethernet performs better when signing is enabled over RDMA. And that's kind of surprising to most people, because when you use signing over RDMA, direct placement is, or the RDMA reads and writes, or RDMA direct placement is disabled. So essentially you end up going through the RDMA send-receive path. And RDMA send-receive buffers are usually small. I believe it's like 4 kilobytes or something on each side. And so RDMA software stack, the SMBDirect layer, has to do fragmentation and reassembly of all those data. And TCP, most of these cases, it's offloaded on the NICs these days. So it ends up that you lose RDMA writes, and then the additional cost of fragmentation reassembly just kills your perf, and people end up complaining badly, saying like, why does performance so bad when RDMA is enabled? So we thought about it, and we said, oh, okay, people are not going to turn off signing, so what can we do better? So we thought, okay,
Just ignore it.
that wouldn't be good. We said, okay, if you want to sign, well, we've got to provide signing. Why can't we sign or encrypt the RDMA buffers separately? Or rather, why do we want to disable the direct placement? Let's say that we allow direct placement, but we sign the direct placement buffer, or we modify the direct placement buffer with encrypted data, and then still use signing. So that's something which Wen is going to talk about, and I think there will be some benefits. We haven't fully tested it out yet, but it's still a work in progress. So, that's kind of the high-level picture that I want to share. And then now Wen will.
Hey everyone. So Mathew gave a great overview of the new transforms that we're adding to SMB, or planning to add. So why don't we delve more into the documentation and the detail side of the new transform. So let's talk about signing first. And if you're already familiar with how encryption algorithms are negotiated in the current SMB 3.1.1 protocol, this is probably very familiar to you. So for those of you who are less familiar, this is essentially for the client and server to know what signing algorithms each other support. And so before this proposal for signing, we don't have any negotiation go on between the client and server. So basically, AES-128-GMAC is the first algorithm that we're planning to make it negotiable. So what you do is the client basically sends the algorithm count. For now, it's just always 1, and the list of algorithm IDs, and server will select 1, just like it will select just 1 encryption algorithm when you negotiate. Send this negotiation context back to the client. And if you're into the details of the negotiation context, I think the encryption's negotiation context ID is 04, and so we use 08. And yeah, so it'd be better, this would be more useful when we adopt more algorithms than just 1. So the reason, a little bit about the background, we're trying to switch to GMAC, which Mathew sort of already covered. Biggest reasons, of course, performance gain. And GMAC inherently also enforces a nonce, so it basically natively prevents against replay attacks. But in the SMB protocol, we actually have the message ID number, which also serves as a nonce. So this is kind of duplicate, but with algorithm native support, it gives you more flexibility in terms of designs. And as Mathew mentioned, we moved the signature verification logic from the SMB2 layer down to the SMB transform layer, which it's maybe not benefiting everybody, but if you're suspected DOS attacks, for example, faster signature rejection probably benefits you. And so, like Mathew also mentioned, since we are moving the logic down to, including signing and verification logic, all down to the SMB transform layer, it is beneficial to use the same transform header as encryption algorithms, I think here it doesn't quite conflict with each other, because our current encryption algorithms are authenticated encryption algorithms, so which basically means your signing algorithms and encryption algorithms are mutually redundant. So in the MSSMB2 doc, we basically have a flag/encryption algorithm field for this transform header, and currently in 3.1.1, the only defined value is 01, which is encryption. And so now if you just signed your packet, use 02. So I think Greg did.
You should say that's proposed. That's not yet implemented or shipped.
Well, we have a slide in the last saying everything can change.
Good.
So in 2015, I think Greg an intern implemented a prototype for the GMAC. So the performance is really irresistible, I think. So they used the 10 Gbps link, and if it's too small, the blue bar on the left is the CMAC performance, and yellow is GCM, and purple is the GMAC variant of GCM. So basically, around 4x the throughput and around 2x the speed up for cycles per byte. So pretty promising, I would say. And that's, yeah. Sorry, both of them use.
Both uses in the AES instruction, right?
Yeah, they're.
Not dimension option. Both has the other explanation option.
Oh no. Are you asking whether they are?
Between GMAC and GMAC.
I think the question was, do you use the same Intel AES-NI extend the instruction set? Yeah, I believe they do. Because I think the new GMAC, the GCM instructions came in later, I think like 2015 or something, right? So I know that they both use whatever instructions are available. So GCM performs significantly better. Yeah.
So, and like Mathew mentioned, we're implementing the overhaul for signing and encryption over RDMA. And for a quick overview, so basically take SMB RDMA write as an example. You would so the client would want to register an RDMA buffer and send a regular SMB request write packet to the server with the RDMA descriptor it gets from the RDMA layer, and the serve will do an RDMA pull, this is a very simple version of without transform. So with transform, for performance issues, of course, we want to keep using this RDMA pull mechanism, and on the RDMA read, that's RDMA push. So what we do is essentially add a transform layer between the client, or for write at least, between the client and the buffer registration. So what you do is to encrypt the buffer first, and then you actually register or signed buffer, and then you actually register the encrypted or signed buffer, and you send a slightly modified write request to the server to give it more information on the transforms, and then you just register it and let the server pull the buffer as if it's just a part of the RDMA protocol. And then you, on the server side, because you added additional information in the SMB write request, you would be able to decrypt or verify the buffer. And how will we do this in the SMB2 write request? So if you are familiar with the channel types that's in the existing SMBD document, we have a V1, which is pretty well defined, and a slight variant of V1, which is the remote invalidation of the registered buffer. So with this change, we're introducing a new type, 03. So this is what the current request write packet looks like. So what we do is essentially with the transform, to support the transform, we need signature and nonce, that's the least. We include the original message size to sort of in case any transforms would change the data size. And then, so about the channel offset and channel length, the reason they're here is because if you recall the SMB2 request write, the structure, they actually have a channel offset and channel length that's describing the offset from the SMB2 header all the way to the beginning of the RDMA descriptor. So with this transform descriptor added in, we actually modify the semantics of you shouldn't call it channel offset and channel length, the offset and length field in the request write to actually point to the beginning of the transform descriptor. And then you would get the actual offset from the transform descriptor to the RDMA descriptor in the channel offset and the offset field. And then, so the last field, the channel, is basically, that's a V1 or V1 invalidate, not 6. So that's basically your old channel types. So this new type is, you can think of it as a pseudo type. It kind of wraps the existing 2 types into that field. So, which means your request write structure, you're going to have 0.3 as the channel field. And you basically have a little range for signature nonce, and the offset are both, all of the 3 offsets are calculated from the beginning of the transform descriptor in this design. So this is the write, and the read is very similar, except that since you don't, the client is responsible for sending over the RDMA descriptor, in your read response, there's just not that. So basically, your channel offset length and channel should be reserved as far as I believe. So yeah, so that's RDMA with transforms. Yeah.
So how does it interact with the hardware? So are you just encrypting the buffer first? And
Yeah,
transfer that buffer?
you sort of just encrypting or signing software, and then. Oh yeah. So the question is how. So where does the encryption and signing happen? Are they in hardware, or how do they interact with the hardware? So I think, so the idea is, since we don't have any hardware to offload these calculations to, so you would have to pay a little bit of overhead to kind of encrypt or sign them first, and then you register the buffer, the memory buffer, and then the rest of it should have this basically the same performance as a regular SMBD. Does that? So, and then on to compression. So quick correction first. I think I mistakenly said that the negotiation context ID for the encryption was 04, but that should actually be not 04. I'll double check the document, but that's actually 04 is for compression. And so as you can see, negotiation pretty much is the same with a tiny difference, which is, so for signing encryption, there's probably no good reason for you to sort of negotiate down to a set of algorithms. So if you want GMAC, you use GMAC for all your traffic in that connection, but you don't kind of mix them. But with compression, it doesn't actually matter that much. And especially beneficial if you have a set of negotiated algorithms, because which I'll demonstrate later. Because if you have, say, compressible data, you probably want to use a more algorithm gives you a better compression ratio, and vice versa. So you can sort of dynamically, the application can sort of dynamically adjust based on how compressible the data is, and I'll show that a little bit later. So right now we support 3 compression algorithms, and that's defined in MXXCA. So, like I said, so the server would respond with just n algorithms instead of just 1. And so once negotiated, when you send packets, we want you to be able to say, hey, this packet is compressed with Express, the next one is compressed with Express Huffman. How do we do that? You probably already guessed. We are using another transform header, but instead of using the 52-byte heavy version of the regular transform header, we designed a compact one, because compression essentially doesn't need much, and we made it 8-byte aligned. So we'll have a protocol ID just like your transform header and your SMB2 header. will have original message size because compression, you want it to change your message size, right? So you want to keep it original. And algorithm, like, so that's how you'll be able to tell, this packet is compressed with this algorithm, so the receiver will be able to decompress. And so with this new transform header, there's basically an interop issue. Well, with compression and signing or encryption, you would introduce this issue anyway. So how we do this is we kind of layer them out. And you would compress first, because if you encrypt first in compression, or if you encrypt when you compress and encrypt, you want to compress first, because if you encrypt first, your compression won't give you much benefit. So, which means so you have your payload, including your SMB2 header, and your compression will always be the inner header. And then the outmost goes with your SMB transform header. And although it might not matter that much with signing plus compression, but for conformity benefits, for now we designed it to be just this way. So basically compress and then sign. So it's actually, with software compression, well, you may or may not like it because, well, first of all, it consumes CPU. So if you're running heavy workloads, you probably don't want to spend most of your CPU cores doing compressing work for your networking. And when it's a software compression, well, it'd be ideal if you can offload it to some NIC that supports that. But when it's just software compression, the performance usually won't keep up with too high bandwidth. So most use cases with our experimentation is with, if you're, on a Wi-Fi network or any lower bandwidth network. So we tested the performance with basically two groups of data: pattern data, which means they're more compressible, and random data, which are less compressible. So first test is using 100 megabit. So left side, the gray ones are your basically theoretical max of your bandwidth. So with pattern data, well, the extreme form of pattern data will be all zeros. That's not all zeros will be much faster than that. So that's sort of an outlier. So pattern data is like A, B, C, D, and so on and so forth. So, which is probably extremely compressible as well. So we actually got 4x the throughput on a fairly old hardware. It's probably from 09, the W3520. And so which means your CPU could probably push more. And then random data, we got a 1.68x speed up. So and then we tested with 200 megabits just to sort of show another point, which is you can see the trend that if you can see it on the left side, pattern data, you have 100 as your baseline, as 400 when compressed. I'm sorry, and then when you double the bandwidth, there's not much gain when you compress, which means probably hitting the CPU or whatever bottleneck is the bottleneck. So, and same with on the right side, I think with my personal experience in this setup, it probably tops out between 200 megabit and 300, which is still pretty good if you're on Wi-Fi network and you don't mind using your CPU for this. So, but for future, we might have to think about like offloading to mitigate the CPU usage and the sort of low bandwidth keep up. Yeah.
Can you, I'd have to look back and think about headers, but is it possible that this
adaptive because you don't want anyone to have to say, oh, I want to store network and do compression now. You want it to automatically adapt if it can. So you thought about making how do you make that happen?
So the question is, can we make the compression algorithms adaptive? Am I correct? Like,
Not the algorithm, as in turn on compression.
so whether to use the compression or more, I would say what algorithm is to use, because essentially if you look at the Express Huffman, and actually forget about LZNT1, that's more legacy than that. So Express and Express Huffman is basically Express is best for if your data is medium compressible, and Express Huffman gives you a better compression ratio, but slightly worse throughput. So I had that similar thought than you when I was looking at this, but I personally haven't experimented with whether, if I have pattern data and I use Express Huffman, that would make more sense than if I use Express. What I'm trying to say is there's probably a pretty complex heuristic that we have to study
Yeah, I was
here.
just thinking about if you know these
Yeah.
speed of it, you start doing compression.
The thing about you mentioned the speed of the,
Yeah.
like the connection.
Set it up, say what?
You can simply not compress, you just don't throw the header of the transform header out. And not
Yeah,
compress.
so you kind
Right,
of.
you have to negotiate the algorithms up front,
Yeah,
but then you're not.
that is adaptive, yeah. You can make it adaptive. Yeah, that's what I thought.
So you're basically toggling off on a packet by packet basis.
Yeah, that's what I thought.
You can leave the transform header out.
Yes.
Don't compress, you're running straight SMB.
So actually,
It's negotiated and ready to use if you choose to.
yeah.
Yeah, it's a matter of
Policy is
checking the
different,
round
but
trip time.
you can express it on the wire, message by message.
Yeah, I think
Actually, one point I forgot to mention is the current heuristic. There's one current heuristic, which is if the compressed payload is bigger than the original payload, or you actually plus the size of the transform header, which is a pretty conservative, heuristic, you would not apply the transform header. But I totally agree with you. There's a lot more play that we can, experiment with.
And yeah, I think the other thing is we didn't even, we in fact initially thought about making it a shared property, but then we thought, well, it doesn't make any sense to make it a shared property because it's totally dependent on the data that you have, right? So it's got to be some intelligence on the client as far as I think, maybe based on the file type or the file extension or something of that sort. And then maybe if you attempt on a particular file handle, you try to compress, it doesn't compress very well, then just turn off compression for that file. And it's got to be something like that. And the other thing I wanted to call out is it's not just for files. We, in the data center, for example, we use SMB3 to live migrate VMs from one node to the other. The memory of a VM, we copy over from one node to the other. Memory of VMs are mostly like, there are zeros, there are a whole bunch of zeros in all of them. So those things do compress well, and in fact, they have been asking us for that kind of a feature. So, in fact, I don't think it's called out here. We might even add a specific, like a tag or something saying that it's just a buffer full of zeros, even rather than just trying to compress it. So, it's a possibility.
Retrofit to the school, that to the school as RPCs.
There's one more slide, right?
Okay. All right. So that's most of the content that we had. And I just want to emphasize the first point again. This is all work in progress. There is no official protocol document which Tom has signed off on or anything. So some of these things will change and can change, will change. And when we are ready to ship it, obviously we'll put it into MSSMB. And this is just a look ahead into what we are thinking about doing and what we are going to productize possibly.